The regression equation. Scatterplot. A scatterplot is a graph of data from two quantitative variables of a population. In a scatterplot, we use a horizontal axis for the observations of one variable and a vertical axis for the observations of the other variable. Each pair of observations is then plotted as a point. Here I have an example of a scatterplot. We have weight in pounds, which is the x-axis. I have hash marks at 10, 20, 30, 40, 50. Then I have height in inches for the y-axis and hash marks at 10, 20, 30, and 40. My data are dots with an x of weight and a y of height. The data points look like they move up from left to right, so they kind of form a line. Least squares criterion. The least squares criterion is that the line that best fits a set of data points is the one having the smallest possible sum of squared errors. Regression line and regression equation. Regression line, the line that best fits a set of data points according to the least squares criterion. Regression equation, the equation of the regression line. Here, our x-axis is age in years, with hash marks from 6 to 18 and marks in between at each integer. For my y-axis, I have reaction time in seconds. It starts at 0.3, then we have 0.4, 0.5, 0.6, 0.7, 0.8. Our data clusters around each age in years and, in general, moves down from left to right. Then we have a line of best fit that also goes down from left to right. Notation used in regression and correlation. For a set of n data points, the defining and computing formulas for S sub xx, S sub xy, and S sub yy are as follows. Quantity, S sub xx. Defining formula, sum of, open parenthesis, x sub I minus x bar, close parenthesis, squared. Computing formula, sum of x sub I squared minus, open parenthesis, sum of x sub I, close parenthesis, square, divided by n. Quantity, S sub xy. Defining formula, summation, open parenthesis, x sub I minus x bar, close parenthesis, open parenthesis, y sub I minus y bar, close parenthesis. Computing formula, summation, x sub I times y sub I minus, in parentheses, summation of x sub I, in my other parentheses, summation y sub I. After we multiply those, we divide them by n. Quantity, S sub yy. Defining formula, summation, open parenthesis, y sub I minus y bar, close parenthesis, squared. Computing formula, summation, y sub I squared minus, in parentheses, summation, y sub I parentheses squared, divided by n. Regression equation. The regression equation for a set of n data points is y hat minus b sub 0 plus b sub 1 x, where b sub 1 equals s sub xy divided by s sub xx, and b sub 0 equals y hat minus b sub 1 x bar, which also equals 1 over n, open parenthesis, summation y sub I minus b times the summation of x sub I, close parenthesis. y hat equals b sub 0 plus b sub 1 x, which is basically slope-intercept form of a line, where b sub 0 is your y-intercept b and b sub 1 is your slope m. You need to make sure that you specify your regression equation as y hat, since y equals means you have a line that perfectly fits your data, whereas y hat means we have a line that best fits our data. Response variable and predictor variable. Response variable, the variable to be measured or observed. Predictor variable, a variable used to predict or explain the values of the response variable. Criterion for finding a regression line. If the data points do not appear to be scattered about a line, do not determine a regression line. So here I have 3 different graphs. My first graph, which is the one on the left, I have data points that go up, then are constant for a little while, then go down. Those data points best fit the shape of a parabola. So for this data set, I cannot determine a regression line. My second graph, which is in the middle, has several data points and they move down from left to right. These data points do appear to be scattered about a line, so we can find a regression line. For my third graph, which is to the right, my data points look to form a circle. Because they're in a circular formation, I cannot determine a regression line for this data set. Example. Use the given data to do the following. Find the regression equation for the data points. For our table, we have x and y. Our first point is 4, 8, then 1, negative 1, 5, 9, 2, 2, and 3, 5. We need to find the regression equation y hat equals b sub 0 plus b sub 1 x, where b sub 0 is the y-intercept and b sub 1 is the slope. Going to our calculator, we want to type in our data, stat, edit, enter. L1, we want to type in our values for x, 4, 1, 5, 2, 3. In L2, we want to type in our values for y, 8, negative 1, 9, 2, 5. Now we want to find the regression equation. Stat, over to Calc, and we have 2 options to find a regression equation. One is number 4, where the linear regression equation is in the format of ax plus b. Arrowing down. Our second is number 8, linear regression, where the format is a plus bx, where a is the y-intercept and b is the slope. We're going to use 8, linear regression, since it better matches the format of our equation. Enter. Our x value is in L1, second, 1, comma. Our y value is in L2, second, 2, comma, and it would be helpful if we had our regression line in y equals. Go to VARS for variables, over to y variables. Since it's a line, it's a function, enter, and we want that function to go in y1, enter, enter, and we have our line for linear regression. A is negative 3.2, b is 2.6. Since our format in the calculator is y equals a plus bx, a is the y-intercept and b is the slope. Y hat equals negative 3.2 plus 2.6x. Continuing, graph the regression equation and the data points. Going back to our calculator, y equals will show us our line. I can tell that my plot is turned on because plot 1 is highlighted. I can also check this by going to second y equals, enter, on is highlighted. I want to make sure I have chosen the scatter plot for type, X list for L1, Y list for L2, and then you can choose the size of your dot. Next, I want to go to my zoom menu, and number 9 is zoom stat. That works best for scatter plots. Enter. And I have a graph of my scatter plot with my linear regression line. For this graph, the red dots represent the data and the blue line represents the regression line. The x-axis is from -2 to 10, and the y-axis is from -10 to 10. If the calculated graph needs to match this, use window to adjust the maximum and minimum points on each axis. Going back to our calculator, window, xmin, type -2, xmax, type 10, move down to ymin, -10, ymax, 10. Graph. And now it would be easier to match this to a graph with a scale of x from -2 to 10 and y from -10 to +10. Example: following are age and price data for 8 randomly selected ambulances between 1 and 6 years old. Here, X denotes age in years and Y denotes price in hundreds of dollars. We have data for X and Y. The points are 6, 280, 1, 400, 6, 255, 2, 350, 6, 265, 2, 365, 4, 310, 5, 305. Find the regression equation for the data points. Our regression equation is y hat equals b sub 0 plus b sub 1 x. B sub 0 is the y-intercept, b sub 1 is the mean. Again, we use y hat to denote the regression equation. Going to our calculator, to type in our data, stat, edit 1, over to L1, and we want to type in our values for x. 6, 1, 6, 2, 6, 2, 4, 5. L2, we want to type in our values for y, 280, 400, 255, 350, 265, 365, 310, 305. Now we want to find the regression equation, stat, over to calc, and we're going to choose 8 linear regression. We could use 4 if we wanted. We would get the same information. Enter. My X list needs to be L1. Y list is L2. We don't have a frequency list. We want to store the regression equation in Y1. VARS over to Y VARS, one function, Y1. Calculate. Enter. A equals 412.9167. B equals negative 24.167. We want to round to 2 decimal places. Y hat equals 412.92 minus 24.17x. Continuing, graph the regression equation and the data points. Going back to the calculator, we need to make sure we have our regression equation. Y equals, and our regression equation is in Y1. We can see that plot 1 is on, or second, Y equals, stat plot 1, enter. It needs to be on. The type needs to be scatter plot, which is the first one. My X list needs to be L1. My Y list needs to be L2. Choose whatever you want for the mark. Zoom. 9 for zoom stat. And we have our data points with our regression line graphed. Our x-axis is age, and in this graph it goes from 0 to 8 with hash marks at every 2. And the price is Y. It goes from 0 to 500 with hash marks at every 100. If we would like our calculator graph to match this graph, go to Window. Our X-min would be 0. X-max would be 8. X-scale would be 2. Y-min would be 0. Y-max would be 500. Y-scale would be 100. Graph. And now the graphs match a little better. Continuing, describe the apparent relationship between the two variables. Because the slope of our regression line is negative, our line goes down from left to right. Price tends to decrease as age increases. Continuing, identify the predictor and response variables. The predictor is always our value for X, which is the age of the ambulance. Our response variable is the value that we get for Y, which is the price of the ambulance. Continuing, identify outliers and potential influential observations. All the data points cluster very closely to our regression line. There are no outliers and no influential observations. Continuing, predict the value of the response variable for a 3-year-old ambulance. Using the equation y hat equals 412.92 minus 24.17x, so we want to find y hat when x is 3. Substituting into our equation, y hat equals 412.92 minus 24.17 times 3. Calculating, we get 340. The predicted price of a 3-year-old ambulance is $34,000. Example: the following table contains age and price data for 8 randomly selected ambulances between 1 and 6 years old. Here, X denotes age in years and Y denotes price in hundreds of dollars. A regression was performed and the resulting regression equation was Y hat equals 417.33 minus 24.35x. Our data set is when X is 6, Y is 270. When X is 1, Y is 400. When X is 6, Y is 255. When X is 2, Y is 350. When X is 6, Y is 265. When X is 2, Y is 370. When X is 5, Y is 335. When X is 5, Y is 290. Should that regression equation be used to predict the price of a 4-year-old ambulance? The lowest value for our data set for X is 1. The highest value for our data set for X is 6. Since 4 falls between 1 and 6, since our data point of 4 falls within our actual data set, we can use our regression equation. It is reasonable to use the regression equation to predict the price of a 4-year-old ambulance because the age is within the range of the observations in the data set. Continuing with our example, should that regression equation be used to predict the price of a 10-year-old ambulance? 10 is outside the data range for X, so if I were to use my regression equation, it would be more of a guess than a prediction. It is not reasonable to use the regression equation to predict the price of a 10-year-old ambulance because the age is not within the range of the observations in the data set. Continuing with our example, for which ages is the use of the regression equation to predict the price reasonable? It's going to be reasonable to predict price if the value of X is within our actual data set. Since our smallest value is 1 and the largest value is 6, I can write that as 1 is less than or equal to X, which is less than or equal to 6. Recapping the regression equation, a scatter plot is a graph of our data that can be written as ordered pairs. The least squares criterion helps us find our regression line, which is our line of best fit for our data set. Our regression equation is y hat equals b sub 0 minus b sub 1 times x, where y hat represents the regression equation, b sub 0 represents the y-intercept, and b sub 1 represents the slope. The predictor variable is our x variable, and the response variable is our y. The predictor variable is always the independent variable, and the response variable is always the dependent variable.